Okay, good morning, Physics 20. We are going to start talking about some interference patterns. So yesterday we finished off talking about our closed air columns and how sometimes we have different frequencies based off of how our standing waves are interacting with each other. Okay, so now we're going to kind of talk about a couple other different interference patterns, and then we'll move into the Doppler effect. So if we're kind of thinking waves of a ripple tank, we know that, well, waves in water, okay, creates also a wave that we've kind of been talking about if it moves up and down like this. So how we're going to look at this is that our wavelength, okay, again, it's going to kind of be from one ripple to the next, or from the middle of a ripple to the middle of the ripple. Okay, when we're talking about crests and troughs, our crests are actually going to be these lines here, okay, like the actual lines that you're making. So that's actually what you're going to see. When you see that in a tank, okay, if you think about it, what you're seeing is that big kind of upward motion. So it makes sense that those are crests versus like these kind of pieces here. They're kind of wrapping around versus our trough are kind of the divots down into that kind of wave motion. So the empty spaces here are the troughs versus the actual lines are the crests. Now, when we have two like waves that are going to be hitting together, here's some different interference patterns. So this one that we're kind of seeing, if I drop two rocks down, I'm going to have two different types of ripples that are actually going to be making the effect that are kind of going on. So I have two rocks, so I'm going to place them here and here. And as those are going and they're kind of moving through, I see how they're interacting with each other. Okay, but I'm not actually seeing, I'm not seeing the full circles always, because they kind of keep going against each other at that point. Okay. This one here kind of gives you that little like wave, kind of like you can't really fully see it. And it's kind of that same thing because they're interfering with each other. They're canceling each other out, or they have a constructive interference. This is kind of what it would look like if they don't cancel each other out. And we're going to kind of take a look at this picture on your guys' page, and we're going to talk about what those interference patterns are looking like. So this is what you guys should have. So I have a 2-point source interference pattern. This, we have no clue what we're talking about just yet. Okay, when I'm talking about crests, I'm talking about those thick lines. And if you look really hard on your sheet, you can kind of see those thick lines that are kind of moving through. Okay, and then the troughs are those thin lines that are in between there. Usually in a pattern like this, we don't draw the troughs, or we don't see those troughs. Okay, we kind of just see like the constructive interference of your crests, and then the troughs are just really low. However, we're going to show them here so you can see the pattern. Anytime that we see a red dot along this pattern here, those are going to be our antinodes. Okay, those are antinodal lines. Again, antinodes are when it's constructive interference. So this is where a crest is going to meet a crest, or a trough is going to meet a trough. So if you look hard here, at any point you're either going to see two dark lines crossing, or you're going to see two lighter lines crossing. Versus the blue dots, those are our node lines. Okay, this is where a crest meets a trough. And again, we talked about pitch perfect yesterday. She had nodes, there's no noise. Okay, same thing here. There's going to be like no wave at that point. They're going to completely flatten each other out. So that is on our blue lines here, our blue dots, okay, where we see a thin black line kind of crisscross with a thick black line. Our sources, this is kind of where those two rocks were dropped, okay? These green dots here, that's kind of the first interference pattern. Now, this one is already done up for you, and it's kind of hard to kind of take a look at it. However, we're going to draw our own if you flip to the next page. So I'm going to say grab a pen or grab a marker or something like that. But these two empty spaces here, these are going to be our sources. Okay, so you can actually label these as your sources. And then we are going to start with one source. And then how it works is that every other line is going to be a crest, or every other line is going to be a trough. So I'm going to do mine in red. So I'm going to say that these red lines are going to be crests. I'm only going to do one, okay, just so then I see a red line and then I'll see a black line, and I'll definitely be able to see that interference pattern. So I'm going to start, and then I started with a crest. I have a crest, okay, and then the next one's going to be a trough. Then the next one's going to be a crest, then the next one's going to be a trough. Again, we normally don't see these. Okay, however, we're going to kind of keep them just so we can see this interference pattern. Okay, next one's a trough, next one's a crest, skip a line, and then last one here. Okay, so that's for our left source that was there. Now I'm going to deal with my right source, which I'm going to use the same color, and it's also going to be starting with a crest. Then I'm going to skip a line, and then I'm going crest again, skipping line because it's a trough, then I'm going crest, skipping line because it's a trough, and then the last one here is going to be a crest. Okay, now it's much easier to kind of see those interference patterns. Okay, so when I see a crest crossing with a crest or two red lines crossing, okay, that's going to be my constructive interference. Okay, I'm going to actually see this ripple piece, or if I see a trough with a trough, that's kind of like the big divot. So crest and crest is going, trough and trough is crossing, crest and crest, trough and trough, crest and crest, and then trough and trough would be down low. And again, I'm going to find all these points where there's two of the same colors that are crossing. Oops. Two of the same colors that are crossing. This is where our interference pattern is going to kind of build. Double, just finish it off here. Perfect. Okay, kind of you can see that it's going to start curving off because it's going to go in that kind of circle, concentric circle kind of way. So anywhere where I see these kind of dots, this is where I'm actually going to see that full ripple. If you want up for the challenge, you can try to draw it on the side over here. You can kind of draw what is that thing that you would actually only see. But that would be, it's out of my ability to draw that through. I just see these interference patterns, and please know that what you're seeing, this is constructive. Okay, interference. The reason that this is important, okay, is because if we flip to the next page, we're going to start talking about something called the Doppler effect. Okay. When we're talking about the Doppler effect, it's how different sources and how one source versus an observer is actually going to be reacting with each other, things like that. So we can see that right in the center in this area, I have quite a few dots that are kind of happening to us. However, as it kind of gets farther and farther apart, or as it gets more like out here, okay, I can kind of see that these spaces are getting like a little bit bigger between these kind of crests that are kind of happening at that point. Okay, this is going to affect the frequency, okay, of something. This is going to affect like how often you're hearing something, because if this was a sound, I'd only hear the sound, okay, once these little blue dots actually hit me. Okay, so that's going to affect how you're going to hear something. So when we're talking about the Doppler effect, our Doppler effect is going to be when we have a source, okay, that is going to be moving, and this car is going to be moving at a certain speed, but then this car is going to be making a sound. Okay, have you ever been in traffic and you know that when you hear the sirens, you have to move to the right side of the road? That's kind of what we have to do here, okay, except for sometimes, depending on where this vehicle is, it's really hard for us to decipher, okay, is it in front of me? Is it behind me? Like where is the ambulance? Where is the fire truck? Okay, that's because of the Doppler effect. So when a stationary object produces a sound, the sound wave travels in these concentric circles. So it moves perfectly, like in perfect circles. If I were to be standing here, okay, I would hear any time that I get like a blip of the sound, if they were to kind of continue through, any time that it touches me, I'd hear it. And it would sound like a constant sound because they're not moving. However, once we start moving something, okay, once this car actually starts moving, then I'm going to be starting to hear different sounds. So what the Doppler effect is saying is that when an object is moving relative to the observer, so when it's moving towards the observer or towards the receiver, the one who's hearing the noise, the frequency of the sound is going to be a high pitch, okay, if the person is in front of the object versus a lower pitch if it's going to be behind. So you guys don't have this picture on here, so I want you guys to take a second to kind of like do a little bit of drawing of it. So if this was stationary, so if the source was not moving, Okay, it would just have perfect circles around it, and you would hit, like any time that one of these crests would hit you, you would hear the same sound. Because the source is moving, okay, it's kind of moving in the same direction as where these like sound waves are going. So then it's always going to be making, like it's kind of making the frequency here on the end. You can see that it's like a tighter frequency, which we've learned when you have a higher frequency, it's going to be a higher pitch, okay? Because these are all tighter versus these ones at the back, they're much farther apart. So they're going to be, okay, not as tightly wound, okay, which again, when we talked about pitch yesterday, if you have a higher pitch, you have a higher frequency versus if you have a lower pitch, you're going to have a lower frequency. So that's kind of what we're dealing with here. Because it's moving away and we have bigger space, behind you is when you're going to hear kind of a lower pitch of the same sound, even though it is the same sound that you're hearing. What you're perceiving is different. Okay, so I'll give you guys a second to draw that high pitch one. Then the low pitch is just the flip, the backwards. If I was just standing on the back of this, okay, I would be hearing a much different sound than the person who'd be in front of this car. Okay, because this car is moving, the velocity is actually going towards the observer versus this one, okay, it's kind of moving in this direction here versus the observers behind them. Okay, so it's going to be my frequency back here versus my frequency up here. You're going to be perceiving a different frequency. Okay, this variation of what you're receiving or what you're hearing, this is the Doppler effect. So I'm just going to show you if I can switch this. Let's go to this right here. Okay, we have a plane, or if you can kind of take into account, if I click play here, this plane's moving quite fast. You can get rid of this gizmo thing here. This plane is moving at 240 meters per second. Anytime that these red lines are touching this person and that person lights up, that's the kind of sound or the constant frequency that they're going to be hearing. So they're hearing much more up here, so the pitch is going to be sounding louder, versus now the actual circles are hitting them or the crests are hitting them way later. So what this sound, if this was a ambulance, it would sound kind of something like this. As they're coming at them, okay, it's going to sound a little bit different and get really, really loud. And then after they're passing them, even though it's the same sound that's going to, you're perceiving a much different sound that's going on. Okay. So this is the Doppler effect. So the different variations of pitch that you're getting. Okay, that we talked about here. And again, we know that pitch is directly related to frequency from yesterday. Okay, because of the relative motion, the motion that the ambulance is moving at, that the car, the plane, whatever it's going at, okay, because of that motion, it is going to be changing the frequency of the sound. So this is going to be our formula. It's our last formula that we have to learn, and it's on our formula sheet. So we have FD is equal to FS all times by VW divided by VW plus or minus VS. Okay, now what the heck? FD is the Doppler effect, or the apparent frequency. This is the frequency of what is heard. Okay, so this actually changes. Okay, the frequency of the source, now that is the actual frequency. Okay, so the frequency of the sound is giving off this. So the speed of sound in air is a very typical one. Okay, the speed of sound in air, it doesn't change, but the Doppler effect, the apparent what you're hearing, that's what's changing. Then you have VW. This is the speed of the wave. Okay, so this would be your sound speed. Okay, versus our frequency from above. And then the speed of the source would be the vehicle speed. Okay, this is how fast the person driving or how fast the object that is actually making the sound is going. Okay, now this is the piece. This formula can be switched into a plus or minus depending on what is happening to what's happening with the car and to the receiver or the observer that's kind of going on. It's kind of backwards of what we're used to. The speed of the sound, the speed of the source, Vs, okay, is going to be positive if it's moving away from the receiver, and it's going to be negative if it's moving towards the observer. So it's kind of like when we think moving toward, we think that's positive. No, it's going to be negative this time. So they're going to be flipped. This is going to depend on what this is going to be. Okay, so we just kind of have to be, this is the piece that is the memorization piece, so we need to make sure that we know. So let's do an example. So you have a whistle that has a frequency of 625 hertz, and it's traveling at 29 meters per second towards a stationary observer. If the speed of the sound is 337 meters per second, what is the apparent frequency of the sound as heard by the observer? The reason that's important to know that it's a stationary observer is that later on in a higher level of physics, it also is going to change if we're moving towards a different sound or away at that point as well. Okay, so there's so many, there's 1, 2, 3, 4 different variables that we need to know in what we're solving for. So let's figure out what we have. So it says a whistle has a frequency of 625. Okay, that is the whistle's true frequency. It's the frequency of the source. So that's my Fs. Okay, so my Fs is 625 hertz. Okay, it's traveling at 29 meters per second. So that is going to be our velocity of the source, our speed of the source. It's 29 meters per second. Okay, and it says toward. Okay, because it's toward, it's going to be minus in our equation. Okay, you want to keep it as 29, but then in our piece of FD is equal to Fs is equal to VW over VW and then Vs, we know that it's going to be minus our Vs. I don't know why I put another equal sign there. Cross this out here. Okay, so you can either put as that's negative 29 going in there, or you just know that you have to minus it in that equation. If the speed of sound is 337 meters per second, what is the apparent frequency? So the speed of the sound is actually the speed of the wave that we're going to be seeing, or hearing, sorry, that's 337 meters per second. So what's the apparent frequency? So what is the frequency that I'm hearing? That's my Doppler effect frequency that I'm looking for. So this equation is nice, I don't have to rearrange it. I'm going to say FD is going to be equal to 625 all multiplied by my 337 divided by 337 minus 29. And I just need to type this exactly in my calculator. Please do not think that I can cross out these 337s. You cannot. That's kind of like the same thing as killing kittens. Okay, what we say before, it's not going to be working that way. Okay, the answer I get in my calculator, 625. You guys should be typing it into your calculator too. Okay, so I get my FD is equal to 683.847, so on and so forth. So with 2 sig digs is what I want. My FD is equal to 6.8 times 10 to the 2 hertz. This is the frequency that I think I'm going to be hearing as the observer. Okay, so now that you should know what this is, I'm going to show you guys this video of Sheldon Cooper.
Not before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Okay, I really hope that video worked. If it didn't, I'll get Mr. Rook to show it to you a different way. But this is our Doppler effect. We're all done. You are officially all done learning Physics 20. You have all the knowledge. So today in your textbook, our textbook questions are going to be page 432, numbers 1 through 4, and then page 434, numbers 2, 4, and 5. I am unsure of the orange booklet questions that I want you to do as of right now, but if you guys look on your OneNote after, I'll have them beside this piece right here. Okay, on Tuesday, we're going to finish our lab. On Monday, you guys will be doing some questions based off all of these pieces. But you are all done Physics 20, all learning Physics 20, which is exciting.